Hello, Pre-AP Chemistry. How are we doing today? Hopefully y'all are doing well. Today we are going to be finishing up Unit 11 over thermochemistry, and we are going to be covering what is called calorimetry. So what is calorimetry? Well, calorimetry is going to be this experimental process that we use to determine a temperature change from the system to the surroundings or from the surroundings to the system. So basically what we're trying to figure out is how is energy moving typically during a chemical reaction. All right. So transfer of energy. Now, one thing to keep in mind is we are going to be following the law of conservation of energy, which remember, it says that energy cannot be created or destroyed, but it can change form. And so one of the things that we'll notice is that when we go through a lot of these endo and exothermic reactions, something is going to be losing or gaining heat. And then in return, something else is going to either lose or gain heat. So energy lost equals energy gained. And that's kind of this whole concept of calorimetry, is us looking at this heat, looking at this transfer, and recognizing that if something is losing energy, something else is going to be gaining it. So a calorimeter is basically a device that we're going to use to determine how much heat is either absorbed or released during that reaction. And we call that process calorimetry. All right. And so there's a couple of ways that we can do this. The traditional way that we would do it in like a pre-AP chemistry lab setting is what we call coffee cup calorimetry. And so with that, we would basically use 2 coffee cups, and we would use those to insulate some water and see how much we can cause that water's heat to change. So coffee cup calorimetry, right? Well, the official way would be more of a more contained environment where we could actually make sure that there's no heat being lost into the air. It's all going into the reaction that we're looking at using some kind of, typically a metal container of some variety, right? So what do we do for calorimetry? So let's take a look at this first problem. It says, during the combustion reaction of 2 moles of sulfur, sulfur plus oxygen produces sulfur dioxide, SO2 is formed. The energy released from this reaction is absorbed by 1,000 grams of liquid water. In the process, the temperature of the water increased from 10 degrees Celsius to 81 degrees Celsius. Well, one thing that I do want y'all to take note of is that my water increased its temperature, right? Well, what that tells me is that water is going to be absorbing that energy, right? Well, we know that if something is absorbing energy, then something else is releasing that same amount of energy. And in this case, that sulfur dioxide, in that chemical reaction of the sulfur dioxide forming, we're going to be releasing some energy, all right? So how much heat is absorbed by the water? Well, anytime we are talking about heat change, temperature change, Q equals mc delta T is the formula that we are going to use. And so I know that Q equals my mass, which they told me was 1,000 grams, times the specific heat of liquid water. For that, we can come up here to the top. So we find that the specific heat of liquid water is 4.184. So my specific heat is 4.184 joules per gram degree Celsius times my change in temperature. Now remember, change in temperature is final temperature minus initial temperature. So 81.0 degrees Celsius minus the initial temperature, which was 10 degrees Celsius. Then we would solve. So I would take that, I would plug it into my calculator, and I would find that Q equals 297,000 joules. Okay, so in that process, that sulfur dioxide, the water absorbed 297,000 joules. So then what is the total amount of heat that was released in the reaction? Well, remember that my heat gained equals my heat lost. I've reversed those. Heat gained would be positive, obviously, and then heat lost would be negative. So heat gained equals heat lost. So if my heat gained was 297,000, then my heat lost is negative 297,000 joules. All right? And then it says how much heat was released per mole of sulfur combusted. Now, looking back at my original problem, they said during the combustion reaction of 2 moles of sulfur. So there's 2 moles of sulfur, and those 2 moles produced 297,000 joules, right? So I would take negative 297,000 and divide it by the 2 moles of sulfur, and then that would give me negative 149,000 joules per mole of sulfur. And then that would end up being my answer there. All right, so thinking back along that same lines, along that problem, basically the big idea that we're looking at here is that my energy lost equals my energy gained. So when I looked at this reaction, I found out my energy gained was 297,000. So that tells me that my energy lost is negative 297,000. And if I wanted it per mole, I know there were 2 moles, so I divided it by 2, right? All right, so let's take another look at this problem here. So it says, in the construction of bridges and skyscrapers, gaps must be left between adjoining steel beams to allow the expansion of metal due to heating. If the temperature of a 10-gram sample of iron changed from 25 degrees Celsius to 50.4 degrees Celsius, how much heat did the sample absorb? So what I want you to do is actually go through, solve this problem, and pause your video, and then we will go over it. All right? So looking at this, again, I see that there is a change in temperature. When there's a change in temperature, we're going to use Q equals MCAT. So then I say Q equals MC delta T, where Q equals 10 times 0.449 joules per gram degree Celsius, which I found that back up in my table up at the top, times my final temperature minus the initial temperature. And I found that my Q equals 114 joules. And so that's how much energy was absorbed. Well, if that much energy was absorbed, then we do know that something else lost it. So then the amount of energy lost in that was negative 114 joules. Okay, so now let's put it all together. We know that heat gained equals heat lost in a calorimeter. And so negative Q lost equals Q gained, which rewritten could be negative MC delta T equals MC delta T. Okay, so in that case, heat lost equals heat gained, right? And so we can actually solve it using this way. And this would be the traditional way that we would use calorimetry. This would be the traditional way to solve for a calorimetry problem. So it says if 18.0 grams of granite, which has a specific heat of 0.803 joules per gram degree Celsius, is heated to 85 degrees Celsius and then dropped into 250 milliliters of water at 12 degrees Celsius, what is the final temperature of the system? All right, so we know that this is a mass. This is a specific heat. We've got a temperature. Now, this is going to be the initial temperature of the initial temperature of the granite. And then I have water, which this right here, remember that water, for every 1 milliliter, we have 1 gram. And so this is going to equal 1 gram. So this would be a mass. And then this is going to be the initial temperature of the water. And so what is the final temperature of the system? Now, one thing to keep in mind is that your final temperature should end up being the same. Why? Because we know that energy is going to continue to transfer until we reach equilibrium, until we reach that point to where there is no difference in that energy. Okay? So I know that heat lost, MC delta T, equals heat gained. So what is going to be losing heat here? Well, remember that energy flows from high to low. So what's going to have more energy, the granite or the water? Well, in this case, the granite has a higher temperature, so it also has more energy. So we know that my granite is going to be losing energy. So negative 18.0 grams times its specific heat, 0.803 joules per gram degree Celsius, times the final temperature, I'm going to put TF, minus the initial temperature, which was 85 degrees Celsius, equals the mass of the water, which is 250 grams, times the specific heat of liquid water, which is 4.184 joules per gram degree Celsius. So that over a smidge. Times final temperature, which is again what we're solving for, minus the initial, which was 12. All right. Then I am going to take that and actually start plugging in some numbers. First thing, I'm going to take negative 18 times that 0.803. I'm going to get negative 14.454 times my temperature final. And then plus, because it's negative 18 times negative 85, we're going to get 1,228.59. And then on the other side of the equation here, I have that 250 times the 4.184, which is going to give me 1,046 times my temperature final, minus 250 times negative 12, which is 12,552. So now I'm going to be rearranging my equation a little bit. So I'm going to take plus 14.454 on this side, TF, and then plus on this side, we're going to bring this other side across, so 12,552. And that's going to cancel this out. That's going to add these two up, which is going to give me 13,780.59 equals 1,046, and then we added 14.45 to the TF, and then we added on this side as well 12,552, and so we get 1,060.45 for my final temperature. And then I would divide both sides by this 1,060. And what I'll find is that my final temperature equals 12.9 degrees Celsius. All right, now I do want y'all to take a quick second and let's refer back to what we started with. So my granite started at 85 degrees Celsius. My water started at 12 degrees Celsius. So if we compare how their temperatures changed, the granite's temperature dropped by like 63 degrees, right? The water's temperature increased by 0.9 degrees. Well, why do we think that is? Well, it has two big factors that are working here, right? The first one is granite has a lower specific heat than water. Water specific heat is 4.184 and granite specific heat is 0.803. And so water is essentially a little more than 4 times, has 4 times more in terms of specific heat. So it's going to take a lot more energy, about 4 times as much, to increase the temperature of 1 gram of water. The other factor is how much water we have in comparison to how much granite we have. So I have 18 grams of granite, but I have 250 grams of water. And so because of that, it is going to take a lot more energy to heat that water up. And so that's why we see that big change in temperature. All right, y'all. So I'm going to leave these last 2 problems for y'all to do on your own. Be sure to check your key. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.